modeling, which we didn't do. In that sense, perhaps it fits the schedule for asymptotic modeling in pseudo way, kind of. And before I start, let me just tell one more thing. I'm very proud to present here, and I remember my only presentation in Ukraine and in Kiev in 1989 in Cybernetics Institute with Professor Ivakhnenko, Alexei Grigorievich Ivakhnenko. It was great presentation about cluster analysis, which I made together with Dr. Mirkin. And it's unbelievable that now in 36 years or 37 years, I'm presenting again. So this is really, I feel kind of very interesting thing. Okay, what is the presentation about? We both, Stan and I, worked for many years in different companies in America, at least for 20 or something years, in companies which made different types of modeling. It's called marketing mix models and many other models. All those companies use regression analysis to make different types of predictions, analytics, recommendations to large businesses in order to improve things. That's why regression was and actually is the main instrument which companies like we worked in use. Stan published perhaps, I wouldn't be surprised, at least 150 different papers about regression. I did much less, but also did. It was strongly related with the topic about causality. In fact, all models we used, they were not just theoretical models of regression. We tried to be causal, like to say, if you do this, something will happen then. This is what companies asked from us actually to do. That's why we always looked at regression modeling as a tool to understand causal dependencies. And I published quite a lot about that. Stan also did. So, but finally, after that long experience, we decided to do something not maybe very trivial. Besides of different theoretical features of regression, which are kind of extremely well known, and there are thousands of publications about that, we decided to check different features of this tool on real experiments. So what we did was we just formulated some kind of problem, like what we want to understand about regression, and then we started to check what happens. And then, to our surprise, several things were in quite big contradiction to established knowledge about that, because people use regression around the world, millions of applications, thousands of textbooks, etc. However, something was missed and quite serious. And this is what is this presentation about, what we actually have found. So first, how we did it, what was the design? It's described shortly here, but in words, it's a absolutely traditional linear regression model. We used always number of predictors as 10, and we did them in kind of different way. Some predictors were correlated, some other were uncorrelated. I wouldn't go to the deep story of what means correlation or not correlation, because it will go from the results. Then correlation formulas were obtained using this well-known Cholesky decomposition, like this, the equation 2. And also, I wouldn't go into details. And correlations were given with all those values. So as you see, we experimented with mutual correlations on different levels, almost zero to almost multicollinear things like this in equation 3. So in other words, the data sets and size of each data set was 5,000 observations. The data set was extremely simple. It wasn't like heterogeneous. It wasn't combination of different things, like one half is from one normal distribution, another from another. No, it was just one big data set, which means it looks like it's an ideal kind of case to demonstrate how beautiful regression is, what's said in the textbooks. So this is how it was designed, like this. So the one very important feature was from the very beginning that we set all regression coefficients to be positive. It's usually statisticians ignore this sign, looking at that like it doesn't matter. Of course, it doesn't matter. It could be positive or negative. But why it was very important for us is that when you have positive values and you know they are positive, then you can easily compare the resulting values. If you use, let's say, in generation coefficient in generation of your y variable coefficient 20, and you got, let's say, in estimation process coefficient 25, you can very easy to calculate the difference between 20 and 25 in undisputable way. You just calculate how close they are, and you can make relative division. You can divide it by actual value of 20 and calculate what percentage of deviation exists. And this is a kind of extremely simple statistics, which is always used in engineering, for example, or in many other things when things are measured in a normal way. But it's very rare used in statistics because people prefer much more comprehensive things without that percent-wise understanding. Why for each engineer, it's clear that if real value is 20, but actual value is, let's say, 40, that coefficient is 2 times more, it's unacceptable kind of things. It also directly related with theory of errors in the data, but I wouldn't go there. I mean, later I will mention a little bit that. So what also was used, so those are kind of set coefficients. What also was used, we used different values for the random error in the end of regression. They were different from each other based on values of this standard deviation, which varied from 20 to 200. Of course, those three types of deviations, they created very different situations. Either everything was very strong correlated with y because no random fluctuation, or very slow badly correlated. And I will give some figures a little bit later. So each value of this sigma actually presented different level of the R square, which we could get from the estimation of the regression. Before we go to the results, I would talk very briefly about some mathematical things about that. The first part is more or less standard. This is standard normal system of equations. But what was interesting, that what was a little bit kind of new in that we used those things, those transformations, in order to have so-called, so this is a standard solution, but this is the couple of things which we used in our calculations, which are not that standard. So we calculated this value, which is weight of each observation in their total for each variable. So this is the formula. And then we calculated so-called, and this is important. This is what we are going to use later to explain. We called it reference matrix. What is that? So specific set of equations which is designed as a relation between average values, as you see. So everything here is averaged among themselves. So we can create this type of system of equations, which is where number of equations is equal to number of x variables plus 1, because there is one y variable. And it turned out that this new transformation is it bears very interesting features which have not been investigated before. It's a special kind of hyperplane which goes among all average values in hyperspace. Generally, it's easy to understand. However, we used it for kind of pragmatic purposes, about which I will tell a little bit later.
And what about your errors? Are they uncorrelated or not?
Oh, errors absolutely uncorrelated. They are independently generated as normally distributed values with different sigma. Yeah, they're uncorrelated with original. Yeah,
So
that's right.
correlation may be inside regressors, yes?
Right. All that correlation, where is it? Wait. Oh, here, equation 3. So all those correlations are only inside regressions. 4 levels of different correlations between regressors, between what. So, for example, this group, and we varied that in experiments. Like those variables, they are independent. Those variables, this subgroup is correlated. Correlation was given with that formula, as I said before, and that's it. And this term, E, it's absolutely uncorrelated with anything. It only regulates general level of approximation of the data. Okay? So, okay. There is important feature in that so-called reference matrix, which is over here, which is that it is after division, it's special type of normalization, which means that everything is presented in the same kind of in the same identical unit of measurement. That's why we can go back and forth with those values without thinking about what were original measures of each x variable. And otherwise, we can do anything with this matrix. The only specific of this matrix is that it's very small, because it depends only on number of variables, not on number of observations. So it's like a short picture of everything. And you will see later how it works and why. For example, we can calculate correlations between columns, which looks a little bit ridiculous, because we are talking about correlations between columns, each of which has just 10 values. However, it's still correlation, this kind of things. It has, its important feature is that it's extremely stable, about what I will talk later again. So a couple of other indicators. traditionally, when we calculate different coefficients of regression, we see that they're measured, the quality of that is measured by test statistics. Like so, this is kind of what everybody uses to calculate it. I wouldn't go into details. It's in each statistical package, etc. Another way of directly measuring the precision of coefficients, this is what we are using in our calculations, as I mentioned earlier. Since we have all positive values, we can definitely calculate these simple statistics, like we divide estimated value by generated value -1, and we take it, and so it gives you the relative, in percentage, the relative deviation from the actual value of the coefficient, since we have it. And so those are traditional beta coefficients. I wouldn't go in details. It's well-known statistics, traditional usual regression coefficient, and the fraction between sigma of the regressor divided by sigma of the y. And those things are well known too, that R square is, so this is established relation, which we also used. R square it's extremely useful, but in practice it's rarely used. In my mind, it's one of the very important equations in regression analysis, because it allows to decompose R square by this sum of products, coefficient of correlation between y and x times beta coefficient, sum of those. So we note this as d, and we use those d's, those product of beta coefficients. We use it to do things. So if those things have one important feature, sometimes the sign of R and sign of B are different. Respectively, D would have negative value, and some of them will always be equal to that, but it doesn't allow to calculate relative importance of the variable of the contribution. However, it's undesirable. Ideally, in good regression, the signs should be equal to each other. It's, by the way, the big question. To my surprise, I faced some opposition to this point of view. Like some people, for example, one very well-known specialist for regression told me, well, it doesn't matter. In my mind, it does. Because think about that. If B tells you that angle of the plane is, let's say, positive, but R tells you it's negative, what is the interpretation of this kind of value? The only answer is that we do not care about real interpretation. We do not really care, which is, it contradicts to my feeling of what all that statistics is to be used for. So in my mind, it should have the same sign. If it has different signs, we should redo regression. Of course, it's understandable why they might have different signs, because all those multicollinearity problems. However, in practice, at least I tried to use always with the same regressions which have the same sign. In that case, we can calculate equation 20. So divide each contribution to R square, and sum of those is equal to 1 after that. And so we can say percent-wise what is the importance of each variable. It's maybe
R square, is it positive always?
I'm sorry, R square?
R square, is it positive always, despite
Oh, yeah,
different...
R square is positive by definition. It's coefficient of multiple determination. Yes, it's positive. Yes. And what is new introduced in this paper also, so this 20 and 19, those are known equations. But this one, perhaps not, at least we haven't met it in literature. So it tries to understand the following, that if Since D is a product of two things, it tries to understand how important is contribution of each of those two elements, coefficients of correlation between y and x and coefficient of regression. So since, as I said, they generally might have different values, this kind of statistic is proposed. So what we can do, we can take logarithms of everything, and then after this simple transformation, we might have the decomposition similar to this one. So this 20, which is actually many people use, but in this case, we can say that ydj is large because half of that, or 20% of that, because of r square, and remaining percent of that is z. Sum of those things is equal to 1. If they have different values, we can take absolute value, but in other words, it's another way to further decompose this, further understand what's going on. So first we decompose r square, and then we decompose each ingredient, which is d, contribution of each factor. Here are some kind of statistics which are more or less known. This so-called variance inflation factor, I wouldn't go into details, it's also well-known statistics. And so this equation is known. It's just a reminder how it works. R square is 1 minus variance inflation, VIF, for each variable. And so this one, and we calculated so-called, this is new, this calculated so-called relational index Ri in this way. In nominator, we have squared coefficient of correlation between y and j variable. And here we have this statistics, which is, it's used like this factor. I mean, this equation. So it's squared it shows how important is j variable in general term between x and other predictors. Another way to calculate the similar idea is to calculate so-called, there are two possible ways to calculate it, 25 like this and 26 like that. We called it efficiency indicator. It shows, and calculated in that way, that in nominator we have coefficient of correlation between variable squared. In nominator, we have the same plus average value of other coefficients in there. Actually, it's very simple and very logical statistics. When everybody tries to understand the data, it looks in correlation matrix. The ideal model has independent x between themselves and strongly dependent y and x. So ideally, if everything is in correlation matrix 0, then the general regression is to be considered as just the same as estimations of coefficients will be equal to those which we get in each pair regression. You can, instead of making general multiple regression, we can make n individual regressions. It will be the same, because in practice it doesn't happen. So this statistic shows how close we are to ideal situations, because the less this, the close this value is to 1. Then less this means it's that variable is uncorrelated. In other words, this is very important indicator. We can use both indicators, but then we realize that second indicator, efficiency indicator, is better than the previous one. So now let's see what we got in the very result. I would present them as a set of charts which we got after experiments. So this is, so you all remember what those errors which I talked about before, they tell us about level of kind of determination within the data. And approximate relation between level of error and level of R square is given here in that part of the screen. So you see that if error is depending on that, error 20, it was adjusted. It was adjusted in that in such a way that that error, low level of error, would be responsible for high determination, like 85, 94%. This level, 100, will be something in the middle, 18, 38. And another, this level, it generates much less determination, like 10% or something like that. So in other words, you can consider this as very high determined, regressions, middle, and loosely determined. What we see over here is percent of negative, and so just, and this classification will be always used below. That's why it's important. What you see over here is percent of negative coefficients of regression in different situations with errors. And this is on this X correlation between independent variables. Those 4 levels from 0.5 to 0.95, and so respectively the chart. So in other words, the 3 factors are in play here. Those which are reflected in axis, as you see, level of mutual correlation within the data, level of errors, and also level of coefficients of regression used for data generation. If you remember, X1 was something which had very low coefficient of regression, like 1. I don't even remember, but there is a table over there. And X10 was high correlation of regression. So in other words, what we see here, in that situation, number of negative estimations is very high, about 30%. But by design, we had only positive things. The only true things are positive coefficients of regression. However, regression, traditional least squares method, estimates like this. Other variables, not that much, but it's only when error is very small. Look at this. In this situation, when error is high, the number of negative, which means completely out of things, estimations is huge. It varies from 20% to 40% or even more. So it's first kind of sign that something could be gravely wrong with regression, because this is definitely you cannot, you cannot trust that kind of things. But it works, it shows that way, it gives you the negative correlations, etc. We used also so-called distorted data. I wouldn't go too far in distortion. We made a distortion. Distortion was that we combined 2 data sets in one, in fact. So instead of homogeneous data set, we use heterogeneous with 2 modes, etc. Results are much worse, definitely. So I brought some figures here, it could be much higher results. That's why I wouldn't concentrate on distorted data. In the article, there are more details about that, but it's not critical. So the first conclusion is that regression could give negative results even with minimal level of distortion, of indeterminacy, when error is small. Here are the values. It's 95% confidence levels for t-values with absolute magnitude less than 196. So it is percent of insignificant coefficients. And here is the funny philosophical question. So insignificant in traditional statistical practice considered as insignificant, like we can ignore that, we could not, but we know that all our coefficients are significant by design. Why it tells us it is insignificant? Well, it does. And percent of those, again, depends very much on the value of the coefficient. The variable with minimal value, like 1, so percent of insignificant is up to 90%. X2, which has somehow higher value, has 40% insignificance, so-called. Again, with minimal error. With maximal error, the picture is dramatically worse. It's like many variables have very high level of insignificancy. Practically everything, even if you have maximal coefficient of regression, original regression and generated, so we still, estimation still would tell you it's insignificant. So this is, again, another picture that results are very wrong. Here, instead of 10 or more variables, in order to make a picture kind of more clear, there are just 3 variables, which smallest coefficient and largest coefficients. And it shows the relative deviations. Remember relative deviations, so for what percentage actual value deviates from the estimated value. Average deviation from an actual coefficient, yes. And we see that the actual, so before we used t-statistics, which is traditional way to say, is it good or not? Here is untraditional way, which is not always possible only when you have positive values and you know they're positive. So, I'm sorry. Oh, I'm sorry. I'm making a presentation. Yeah, okay. I'm sorry. Yeah. And we have sharply different things. The higher mutual correlation, the higher level everywhere, as you see, and the higher error, the higher also percent of those average deviation is here. Pay attention that on a scale on the left, it's not percentage, it's times. 2 means 200%. So deviation is, let's say, 2 times. Here, 6 times. Here, it's 10 times. 12 times. In other words, when we measure deviation from actual values, we can be absolutely way off, depending on the picture. And it depends strongly on 2 aspects: how mutually correlated things, as you see on each chart, practically it goes from the left to the up, like especially here. But even more, it depends on the level of errors. So it means that we can calculate coefficients, it's like, which is absolutely different from the real value. Another one, average correlation between predictor and dependent variable. Correlations between those things would strongly depend on the value of the coefficient. The higher those coefficients, 20, 21, and so on, the lower the higher correlations between predictors and dependent variables. This is actually it's like side observation. It's not maybe very critical. Maybe I can just stress one thing, that even when error is minimal, what we observe in the data depends very much on the actual regression coefficients used. And the more errors, the less this dependence is. On a chart, it's clear, it goes that way between panels. So in the first panel is high, in second panel is this. In other words, error for the general regression decreases effectiveness of the estimation of the coefficients. They have to be very high, the coefficients, to be correctly estimated, which usually people do not pay attention to. And this is interesting. This is, we now go to a little bit more complicated things, namely to the reference matrix, which we talked about. So this chart shows that if we calculate correlations between variables for reference matrix, we see very surprising things. They practically do not depend on the level of errors. If you look at this picture and compare that with this picture, you see that clearly. Like previously we had this trend, here we have nothing. In other words, transition from usual to reference matrix allows to select variables with largest coefficients very steadily, firmly. We can say, wow, those variables which have maximal correlations, before we had the troubles with that, now we separate them, which means it's regardless on noise in the data, which means level of that error, reference matrix allows to do this kind of things. So respectively, we can use it as a tool to reduce the number of predictors in multiple regression, which is typical task. Everybody is reducing number of predictors by different things, but this is, it shows that it can go in a very stable way. I guess I can switch, skip this slide, and maybe this slide. I'm just look at the time. It looks like it's not much time left. I don't want to be things. Those effects are usually not kind of considered, but they're very useful. In other words, average share of the coefficient of correlation in complete models. So this is about sensitivity. That those which has strong effect, they kind of, or maybe it's too long to explain. The most interesting part of this chart is that those variables with strong effect, they have identical pictures regardless of noise in the data. It's like they go in this and that. And this is when we try to understand what works better, like traditional coefficients like t-statistics or variance inflation factor, or our statistics and actual things. And when we calculate the correlations between those variables, you see that we calculated it in two ways. Then I guess it's I don't see it would take too much time to explain in details how this is calculated, but let me just stress the entire conclusion that efficiency index, about which I talked before, on effective at least as test statistics, and in many cases just superior. So in other words, it makes a lot of sense. We do not recommend to replace test statistics from analytics at all, but we want to add to that efficiency index, and it will be much more intuitively clear. High efficiency index always means very good predictor. Similar results. What we did, yeah, it's funny results because it's too many results, and I just don't know. I just want to conclude that so this is a different, the same different type of correlations, and then if we make so-called proper model recommended only by t-statistics, then we would have a percent of total number of models. They would be, percentage would be like that. But if we do it average estimation in proper models, then it could be like this and like this. So it's always, in other words, test statistics allows to be really works very well in very rare number of cases determined like this. And when we make estimation differently, then we have much more kind of much more success. And here also how influential variables are determined. Influential variables which we detected using reference matrix, they present much better determination like this instead of other variables which were selected by traditional way. We're talking about just 3 variables. And I guess it's enough regardless on that. So let me just go to the conclusion, because detailed explanation of each chart would take much more time. So what we found finally in all that stuff is that all traditional statistics used in regression analysis need to be considered with big skepticism, especially test statistics and tests for significance. It should be supplemented with different indicators of quality, like efficiency indicator, and perhaps reference matrix as a tool. And then the results of regression analysis will be much better. And this is without even mentioning errors in the data. We made an article with Professor Kukush once, which showed I couldn't have, it's a very special topic, and Alexander Kukush can explain it much better. which shows that there is a special way how to estimate the significance of coefficient of determination in situation when everything is with errors. It's classic. X and Y both have different types of errors. How to distinguish the variance determined by the actual relation between variables and variance determined by the noise. If we add this observation and coefficient recommended in that article, there is special criteria for that, and we combine those two aspects together, then you will see that traditional regression methods will be really very weak kind of instrument, which we cannot rely seriously on. So let me finish on that, and we have maybe time for the questions. I, of course, can answer. Thank you very much.
Thank you for your presentation. And any questions? Then I ask a question. Okay.
Were your results compared with regression?
Mm-hmm.
I'm sorry, I didn't. Where results are
compared with ridge regression.
Ridge regression.
Ridge regression. I see.
Ridge,
no. I got it. No, we didn't make comparison, but I guess Stan can add a couple of things about that. He published several things about ridge regression. Empirically, we don't. Stan, could you add something about ridge regression?
Thank you.
About ridge regression. Classical ridge regression is one parameter ridge. And there are many modifications with couple ridge parameters and even more. And various constraint criteria like sum of squared coefficients or coefficients by absolute values like in lasso or combination of them. All of them work in practically the same way. They reduce possible singularity in covariance or correlation matrix. And that's all. We were not interested in this work to reduce effect of multicollinearity. We wanted to see it, how possible relations between predictors would affect our results. But what is interesting, and I would add in principle, any kind of singularity, closeness to singularity in covariance or correlation matrix, it is important for individual estimation of parameters of regression, but it doesn't matter for prediction. As we know, in predicted values of the dependent variable or in R square, there is no dependence on the level of multicollinearity between predictors. It is known thing. So multicollinearity and using ridge could be important if you want to analyze impact of each particular variable. But if you are interested more in total predictions in R-square, for instance, then it doesn't matter.
Well,
Is it what you wanted to ask, or do you mean something else?
Okay, and
th-
I have a
thanks.
okay. Arnold, are you satisfied with this answer?
Yes, yes.
And
Okay.
I have a question. So, as far as I understood, you used Gaussian random variables for simulation, right?
Right.
Yes, yes,
Gaussian
yes,
random variables for simulation of the
Data.
epsilon error. Yes.
And for X, also Gaussian.
They were uniformly distributed X. Yes, uniformly, that's it.
Yes. But it may be interesting if you try heavy-tailed distributions for X, then you can see some interesting effects with large values or small values for X, and they make influence on your reasoning.
No,
Statistical
absolutely.
reasoning.
Yeah, of course. The way how you can simulate the data, there are a number of ways, and it's like, for example, I believe it's a topic for dissertation. Somebody can seriously simulate very different situations, and it would be a very good book, a collection of different things, different results, and so on, which could be good, как бы сказать, so to say, addition to very theoretical considerations of regression in usual statistical courses, kind of things. Yeah.
For example, if you use Cauchy distribution, then you have no expectation, and then you will face some instability in your design metrics.
That's right. Absolutely. The way to extend this type of simulation, I guess there are so many ways of that. Definitely, we didn't exhaust all possible ways to do things. But this is very typical, what I just showed. My experience shows that when you replace uniform distribution by normal distribution, few things change. It's not dramatically changes, kind of general things. We can definitely do that, but I don't expect that it will be something very seriously changed.
Because both these distribution have light tails. And if you use heavy-tailed distribution, then it will be a real disaster for your analysis.
Most likely. This is what I just suppose, that what we did was more or less typical situation and artificially good situation. Any worsening, any things which are worse, like heavy tails or something like bimodals or many models, of course, would create only more mess. And this is the problem. And I remember the actual data, which I worked a lot with, thousands and thousands of observations. We worked once, for example, for Procter & Gamble, you know, the huge company, one of the biggest in the world. They provide data in huge quantity, and they're extremely heterogeneous. And in that situation, how you understand things, actually all those marketing mix models, it's a very, very big question. So you adjust a little bit here, you lose something there, and then finally it's piece of art, how you create the model, how, you know, it's, that's why what we demonstrated in very pure situation means that in any actual situation, it would be definitely much worse.
Yes, in insurance data, when you have claims, and they typically have heavy tails, and then if
Right.
you have insurance claims, yes.
Dan, I don't remember. Did you work with insurance data or not? I didn't.
Not much, but it's known that the worst kind of data we have there with heavy tails, yes. But special modeling could be used, not linear, of course. For any other distribution like Cauchy or what else, we should try to find some more adequate techniques to model and to predict by them.
Perhaps truncation is needed if you have heavy tails.
Right. The straightforward way indeed is reducing of those tails. But how to take them into account is more complicated, of course. Or to use other criteria, not what we have in linear regression. Apply minimization by absolute values for Laplace or such things.
Okay. And any other questions or remarks? Then I want to make a remark. So in this talk, we observed explanatory variables exactly without any measurement error.
Right.
Yes, and in my joint paper with Professor Igor Mandel, we considered measurement errors in regressors. And the problem becomes much more complicated, and we just invented goodness of fit test, actually, for such models, and published a paper about this. It was goodness of fit rather than significance test, I think, in our paper. Yes. But it would be interesting to develop similar technique as in this talk for measurement error models. And for small measurement error models, it should work, I think. So the proposed quantities should work. One can check, please. It could be another simulation, just to contaminate a regressor with errors and then try your analysis. Could be interesting.
Of course. Yeah, I agree. Yeah. It's a lot of work ahead if somebody would do that.
Okay, if there is no question, then thank you once again for interesting presentation. Yes, and
next. And thank you very much for invitation and for the possibility to make a presentation. It's a very rare case, by the way, that there is the entire hour to make kind of things, because usually on conferences it's 15 minutes and you don't have any time for anything. Here, it's nice that you organize that seminar.
And everybody are welcome to come next week